Hi again, how's it going, everybody? The next section we're going to cover is 7.3. So we did trigonometric integrals last time, and now we're going to do a technique that's known as trigonometric substitution. Sorry, just making sure the camera's all good. So here it's a substitution, but it's a little different than when we did U substitution. So here's just an example so you can see what I'm talking about. So let's say we have the integral like x times a squared minus x squared. Say we have this integral here. Now, if you make the substitution, u is equal to a squared minus x squared, where a is just a constant, it was just a number, so 1, 2, 3, pi, whatever, just a number, then du would be 0 minus 2x, so negative 2x, and then, du over this is dx, and this would allow us to do our integral, because we would get the integral of x root u times du over negative 2x, and then the x would cancel. Now, one thing to notice here is u was a function of x. So the original variable x, we defined u in terms of that. So that's something that we want to think about. Now, say we have a very similar looking integral, but this x is not there. We just have this. Okay, so if we just have that, then we can't do u substitution anymore. In this case, this x here won't cancel out with anything. So this is where the idea of the trigonometric substitution comes in. So we're going to now define the original variable x in terms of a new one. See how this is opposite? So x now will be equal to, so normally we did the new variable is a function of the old one, but now we're saying the old variable is a function of some new variable. It's the opposite process. And for this reason, this is called the inverse substitution. So we're going to let x be equal to a sine of theta for theta in a very particular range of numbers. Notice that if we want to recover what theta is, then we have to divide by x over a, and that's sine theta. So to recover theta, you would say it's the sine inverse of x over a is equal to theta. And then remember that there's a very big restriction on what angles theta, will come out of this. You can only get a certain interval of angles theta when you take sine inverse. And so this is only valid for theta between negative pi over 2 and pi over 2. Maybe I should say in. So for theta in this interval. For theta in the interval negative pi over 2 to positive pi over 2, which was the range of the inverse sine function, this definition can be satisfied because we can get the original angle theta out of this. So the idea is that if we wanted to, we should be able to write theta in terms of x as well. So this inverse substitution, you can tell maybe not will always work out because it relies on the fact that you can take an inverse function, but those are technical details that we'll just kind of sweep under the rug and just go with this. Okay, so you may be asking, why did you make this particular substitution? And we'll see in a second, because if we do this, this becomes the square root of a squared minus, well, if you square this, you get a squared sine squared theta. And now I have to see what dx is. if you take the derivative of both sides, we'll get dx is going to be equal to the derivative of this, which is a cosine theta d theta. So remember, every time you do this, you just take the derivative normally of this and then tack on d whatever the variable is, so in this case theta, and x turns into dx. So then we get a cosine theta d theta out of this. Okay, so we've transformed our integral to this one. And so now, notice that you can factor out this a squared to get this. Then we still have the a cosine theta d theta. And then this, using this property, so if you have an a times b in a square root, you can take the square root of each part and just multiply them. So this becomes the integral of root a squared, aka just a, times the square root of 1 minus sine squared theta times a cosine theta d theta. Okay, so now this a and this a gives me an a squared. And 1 minus sine squared theta, remember from the Pythagorean identity, and this is why we made this substitution, is we purposefully knew this would happen. We knew if we let x be this guy, we would get 1 minus sine squared, because now cosine squared is 1 minus sine squared theta. So we can change this to the square root of cosine squared. So this becomes square root of cosine squared theta, and then just this cosine floating out in front. And then so now when we take the square root of cosine squared, technically we get the absolute value of cosine. So this becomes the reason why the absolute value is there is to take into account the plus or minus. You know, anytime you take the square root of something, it'll be plus or minus x technically. It's not just x. So the absolute value takes into account the fact that there's a plus or a minus. Okay. And then with this a squared, when we did it, we can just assume a is positive. It doesn't change anything if it's negative or not. So we can assume that a is positive. Yeah, so with that assumption that a is positive, that's why we didn't need, when we took the square root of a squared, if it's always positive, what's the absolute value of a positive number? It's just that number. Had it been negative, the absolute value would have tacked on the minus sign. If negative, if a was less than 0. So remember, this comes from the original definition of the absolute value. I'll just use a for this case. It's a if a is positive or 0, and negative a if a is less than 0. So if you want to drop the absolute value symbol, you'll either keep the original thing or you tack on the minus sign, depending on which one of these conditions you fall upon. But because a was positive, we didn't care. You can just drop the absolute value symbol because it's in this scenario. Okay? And then we have cosine theta here, d theta. And now, if we think about it, we said that theta lies in this interval. Theta is some angle between negative pi over 2 and pi over 2. Now, for all of these angles, cosine is actually positive. Cosine of any angle between these two is a positive number, which again means that we can drop this absolute value symbol free of charge. We don't need to pick up a minus sign. And so then we have, oh sorry, this should be a squared. And so now we have cosine times cosine, that's a cosine squared. And now we know how to deal with this integral. This was something that we did in the last section. You would use the formula cosine squared is 1/2 times 1 plus cosine of 2 theta, and proceed from there. So you can see how this thing works out. And we'll do an example real quick of this. And we actually might just do this to completion, why not? Or we'll do a more general version of this here in a second. Because if you remember, the square root of r squared minus x squared, this gave us an expression for the top half of the circle of radius r. So this would be, if you have a circle of radius r, this gave us the top half of it, and then the plus or minus, the minus gave us the bottom half. And that's exactly what we had. We had an a squared minus x squared, a being the radius. So this type of integral can tell us now the area under the curve. So it could tell us the area of a circle, essentially. We can use this to find the area of a circle exactly. And remember earlier in the class, we just resorted to using the formula that we already had, pi r squared. But in this case, we can derive it from scratch. And we'll do the more general setting where we have an ellipse. So an ellipse is basically a circle where these distances aren't necessarily the same. In a circle, this distance a and this distance b are the same. But in an ellipse, they are not necessarily the same. So we'll derive the area of an ellipse, and we'll just see that the area of a circle is a special case of that. Okay. So this is the general idea of the trigonometric substitution. And so we have 3 different scenarios that we're going to want to consider. So one case is if you have, so depending on what expression you have, there's 3 different ones. If you have the square root of a squared minus x squared, like we saw, the substitution that you make is x will be equal to a sine theta. So this will be the substitution we make. And again, remember, there's a condition on what theta can be. Theta has to be in this interval. So theta has to be in that interval. Maybe I should put it to the right. And then this substitution works based off the following identity. So the identity that we use is 1 minus sine squared equals cosine squared. That's the identity that's being used. So we saw how that was used. Now there's 2 more. So now instead, if we have a plus sign, we're essentially going to use the identity 1 plus tangent squared equals secant squared. So using the fact that 1 plus tangent squared, see there's a plus sign here. So if you want this to end up giving you a tangent squared, you would make the substitution x is a tangent theta. So that's the condition there. And then remember, if we want to take the inverse of tangent, that means the angles have to be in this interval. So very similar to sine, except the endpoints are not included. because remember, tangent is not defined at those values. And then last but not least, if we have, instead of a squared minus x squared, we have the reverse of it, x squared minus a squared. Notice that if you rearrange this, you would have that secant squared, 1 minus secant squared. So secant squared minus 1 is tangent squared. Alright, if you subtract the 1 over here, secant squared minus 1 would be tangent squared. And this looks very similar to, something, secant squared minus, whatever. And so this substitution will be x is a secant theta. And then we didn't talk about this too explicitly, but remember the inverse secant function, it's defined in two different ranges. It's theta is either between 0 and pi over 2, or, this pi over 2 is not included, or, let's see, pi to 3 pi over 2. Okay, so that's the condition on theta in this case. So in these three scenarios, we know the appropriate substitution. They're based off of this identity, and this will always give us a nicer integral. So now let's do some examples so what the heck is going on here. So because symbols don't mean much when you haven't practiced, using what they mean. So first up is this integral. Okay, awesome. So now if we think about the table that I just erased, this is the substitution where we want to let x be a sine of theta. Because we have a squared, a would be like 3, right? You can write 9 as 3 squared minus x squared, so a is like 3. So we're going to let x be 3, which was a sine theta. As a consequence of that, dx is going to be 3 cosine theta d theta. Okay, and now let's just make that substitution. So now we have the integral of the square root of 9 minus, if you square this, you get 9 sine squared theta. Right, if you have 3 sine theta and you square it, you square each term. This is using the fact that ab raised to a power p is a to the p times b to the p. So you raise each thing to the second power. So 3 squared is 9, and sine squared is just sine squared. Okay. So this is that, and then we have the same thing at the bottom. We will have 9 sine squared theta, and then dx is 3 cosine theta d theta. Okay, so this looked like we took an easier problem and made it harder, but sometimes, or many times in math, this ends up being a good route. So we'll see what happens in a second. So when we factor this 9 out of here, we'll be left with 1 minus just sine squared. Alright, we just factor the 9 out. And then what you could do with that is pull these apart. So this becomes the square root of 9, square root of 1 minus sine squared. And then this is just 3. So 3 times this 3 gives me a 9. And then this 9 and that 9 effectively just cancel. So this is, without rewriting the thing too many times, what we have. Okay? So then now we use the fact that 1 minus sine squared is cosine squared. And then remember that the square root of cosine squared is just cosine. It's technically the absolute value of cosine, but we know that because theta is between, or theta is in this interval, for these angles, the cosine of these angles are always positive. Because remember, negative pi over 2 to pi over 2 on the unit circle is here. This is negative pi over 2. This point down here, and positive pi over 2. Now if I make any right triangle within these set of angles, let's say we make this one, notice that cosine is the horizontal length, right? The horizontal length will always be positive because it's pointing to the right. So if you make any triangle on this arc of the unit circle, horizontally you're always going to the right, meaning cosine will be positive. That's one way to think about it. So it's always positive. That means I can drop the absolute value symbol for free. I don't have to tack on a minus sign. And then this cosine times that cosine gives me a cosine squared. Okay, so yeah, this does look not too bad at this point. And then we know that cosine over sine is cotangent, so cosine squared over sine squared is actually cotangent squared. Okay, so long story short, this goes to cotangent squared. So then now we have to think about, what's the integral of cotangent squared? And to do this integral, because we don't know what just cotangent squared is. So we know that the derivative of, tangent is secant squared. And we know that the derivative of cotangent is negative cosecant squared. And because of that, we get the integral formulas. If you take the integral of both sides, cancels out here. These integral derivative cancels out here, and we have these. So we know that integral of negative cosecant is cotangent, but we don't know what cotangent squared. So now we're going to use another identity to make the cosecant squared term pop up, essentially. So we're going to use the fact that, so sine squared plus cosine squared is 1. Now, if we divide everything by sine squared, we get this over that is just 1. And then cosine squared over sine squared is cotangent squared. And then 1 over sine squared is cosecant squared. And that's really nice because now we have a relationship between cotangent squared and cosecant squared. We can see that cotangent squared, what we have, is cosecant squared minus 1. And so we're going to make that substitution. So we're going to replace cotangent squared with cosecant squared minus 1. Because right, if you subtract the 1 to the other side, you get this. And now we know how to do each of these integrals. Because this will break up into the integral of, so we can do it part by part, right? So we saw that the integral of negative cosecant squared was equal to cotangent. So if you multiply both sides by -1, you get this. The integral of cosecant is just negative cotangent. So that one is negative cotangent. So this is negative cotangent. And then the integral of just 1 is going to be theta, whatever that variable is. Because, if you take the derivative of this with respect to theta, you get 1 back. And then, the plus c. Okay, so this is good, but we're not done yet, because our angle theta is not the original variable x. We'd like our answer in terms of the variable x, the thing we started with. So how do we fix this? And this is a really cool trick. So looking at this original substitution, we know that according to this, x divided by 3 is the sine of theta. Meaning, if I make a right triangle and I label this angle theta, the opposite should be x and the hypotenuse should be 3. Now, if you use the Pythagorean theorem, that would mean that 3 squared, let's call this y, 3 squared should be equal to y squared plus x squared, meaning that y squared should be 9 minus x squared, and y should be the square root of that. So we know what y should be. This should be the square root of 9 minus x squared. And that's fine. You may say, oh, well, there's still an x here. Well, x is just a variable. We don't know what x is, so it's okay for the x to be there. But what we do know now is that we can rewrite this in terms of x's, because now negative cotangent theta minus theta plus c is, well, what is the cotangent of theta according to this? Cotangent is adjacent over opposite. So it's the adjacent divided by the opposite, so negative, because of the minus sign here, negative this guy all over x minus, okay, and now you may be wondering what theta is. Well, theta, according to this, is the sine inverse of x over 3. So minus sine inverse of x over 3 plus c. And this is the final answer. So this is equal to the integral that's the final answer. So yes, there's a lot to go on here. It's pretty complicated. But hopefully the idea makes sense. And with enough practice, we can, hone this down and be comfortable with it. Okay, and so now let's maybe do one more example. And we're going to motivate this geometrically. So like I was saying earlier, the equation of an ellipse is very similar to the equation of a circle. It's just slightly modified. So this length is A, and then this length is B. If those are the two lengths, drawn a little poorly. I should say from here to here. So this length is A. So that length is A, this length is B. The equation of such a ellipse is given by the following equation: x squared over a squared plus y squared over b squared equals 1. Now notice that if a and b are the same, and they're equal to this magical thing called r, aka the radius, then we have a circle. In this case, the equation would turn into x squared over r squared plus y squared plus 1, and then when you multiply both sides by r squared, it would cancel out in each of these. Cancel, cancel. And you would get the equation that we established at the beginning of the class, the equation of a circle. So the circle, yes, is definitely just a special case of the ellipse. So if we can get the area of an ellipse, we can get the area of a circle. So this is really cool. We're going to derive the area of an ellipse and a circle using calculus, which is quite amazing. So the idea will be this. We'll find the area of this piece here and multiply it by 4 because of symmetry. Because these are 4 equal looking things despite the way I drew this. So if you multiply this answer by 4, then you have the thing. So how are we going to write this? How do we write this in terms of calculus? What expression will give me the area of the blue thing here, this blue area? Well, we know it's an integral, and we know that we're going to go from, this is the origin, and then this is a comma 0, because you go a units to the right to get there. So we're going to start at x is 0 and end at x is a. And then what is the equation of this top branch of the ellipse? It's similar to when we did it with the circle. So what we're going to do is, first we need to find an expression for that top branch. So if we have x squared, okay, so what we can do is we'll subtract this over to get y squared over b squared is equal to 1 minus x squared over a squared, and then multiply both sides by b squared. So it cancels out here. When we get this there, we'll get y squared is going to be equal to, when we distribute, b squared minus b squared over a squared x squared. And then we take the square root of both sides to get this. Okay, so that'll be the equation for the top branch. Now this is nice, but we can make it look nicer, right? It's the top branch because plus or minus, we'll take plus to give the top. So if we do a little bit of more algebra, we can make this look slightly nicer and more in a form that we're gonna want to see. Because remember, the trig substitution has a very particular form. So now if we have this. So what we're going to do is we're going to factor out, first we'll factor out a b squared to get 1 minus x squared over a squared. So then this b comes out, and because it's positive, we don't need an absolute value symbol. So it'll just be b times this. And now we're going to factor out a 1 divided by a squared. So if you pull out a 1 over a squared, remember when you factor anything out, you end up dividing each term by it. So if we take 1 and we divide it by 1 over a squared, that essentially just gives us a squared. So this is a squared here. Notice when you distribute this back, it cancels out to give you 1. And then with a similar reasoning, this just becomes minus x squared. And then again, you could split this square root, and when you take the square root of 1 over a squared, it's just 1 over a. So this gives us b over a root a squared minus x squared. And this is what we like to see. This is a little nicer. Okay, so that is going to be the expression for the top branch of the ellipse, and that's what we're going to do. We're going to integrate from 0 to a of the function here, so we're picking up the area under the curve right here, because we're going from 0 to a. If we went from negative a to positive a, we'd be picking up this area, but we don't want that. We're just going to do the quarter area. So then this is b over a. So we have, a squared minus x squared. So we have that. So this will be the area that we're looking for, which is really nice. And then earlier in this video, I worked out basically what the square root of a squared minus x squared would be essentially up to a certain point. Remember, we stopped. But this integral, see this b over a, we can just pull out in front. And then we're left with this guy. And remember, we make the substitution, x is a sine theta here. So that dx is a cosine theta d theta. So then this turns into b over a so x squared becomes a squared sine squared. And then remember that we can factor out this a squared. Just get 1 minus sine squared. And then we pull this apart, so this is just root a squared times this times a times cosine theta and then the square root of a squared is just a, so the a times the a is a squared, and like we said, this becomes the square root of cosine squared, which again is just cosine, so this cosine times cosine is cosine squared. So we're left with that. And now this a 1 over a times a squared will just leave an a in the numerator. So this becomes ab integral from 0 to a of cosine squared theta d theta. Okay? And so we're close to what we need. So if we pull this up here, we have AB. And then remember, we're going to use the fact that cosine squared is 1/2 times 1 plus cosine 2 theta. We're going to use this identity here. So we have AB integral from 0 to a of that 1/2 multiplying both of these will pull out in front. So you get this. And then we have 1 plus cosine 2 theta d theta. So then this is AB over 2. And then the integral of, just this 1 here is going to be just theta. And then the integral of cosine 2 theta, remember we said the integral of cosine kx was 1 over k sine of kx. So this will be 1/2 sine of 2 theta. Now I've written 0 to a lot, but that's not the correct limit of integration for theta, right? This was for x. So we have to fix this. Either we have to substitute back, or we're going to have to fix this. So either one. So if x is going to be equal to a sine theta, then that means that when x is equal to a, so if x equals a, this means what? A is equal to a sine theta. And this means that 1 is equal to sine theta, which means that we're looking for the angle whose sine of the angle is 1, and that's pi over 2. So the top limit of integration is pi over 2. So all along these should have been pi over 2's. Sorry, I forgot to do that. I omitted that. And then let's figure out what the bottom limit should be. So now if x is equal to 0, this means that 0 is equal to this, which means if you divide by a here, you get sine theta equals 0, and this means that theta is equal to 0 actually. So 0 actually stayed 0. So these are the actual limits of integration, if we don't want to substitute back. And it's better to not, because remember, to get theta, you have to do all this, you have to draw that right triangle and do all this stuff. So it's easier to just do this when you have numbers. Just find what the new variable should be. Okay. So then, this ends up being AB over 2 times, so when you stick pi over 2 in here, you get pi over 2 plus 1/2 sine of 2 times pi over 2, but 2 times pi over 2 is just pi. So this guy, maybe let me put brackets around this. So we take this minus, stick 0 now, 0 plus 1/2 sine of 2 times 0 is just 0. Okay, and a lot of these terms are 0. Well, this is just 0. The sine of 0 is 0, and the sine of pi is also 0. So all that's left when the dust clears is basically just the pi over 2. So the pi over 2 is left. So yes, we're just left with pi over 2, which is going to be pi AB all over 4. But remember, this was the area of this guy. Just the quarter of the ellipse area. So if we want the actual area of the ellipse, we quadruple this. So as you quadruple this, that means you lose the 4, right? Is the very famous formula pi AB. And as a consequence of that, if a and b are the same number r, then the area is pi times r, which is again the famous area of the circle. So this is very amazing. We can, using this trigonometric substitution technique, we derive the area of an ellipse, which immediately gives us the area of a circle. So that's very cool. Okay, so now that we've seen some examples of the substitution of the form a sine theta, let's see some of the other ones. So this next example is going to be the integral of 1 over x squared times the square root of x squared plus 4. Now again, it's worth it to notice that integration by parts or u substitution won't help us out much here. So this is why we use this novel thing. And so now look at this square root. This square root is in the form x squared plus a squared, where a is 2. Right? 2 squared gives us 4. So we have an integral in this form, and when we had that, the substitution that we made, because of the fact 1 plus tangent squared equals secant squared theta, we made the substitution x is equal to a, so 2 tangent theta. So that's the substitution that we're going to make. And because of that, we get the dx is 2 secant squared theta d theta. That's another consequence of this, because the derivative of tangent is secant squared. And then remember the condition on theta. Remember, this says, we have to keep this in mind, theta in this interval. So theta is in this interval. Okay, so in doing that, what does our integral transform into? It becomes the integral of 1 over, well, x squared is this thing squared, so 4 tangent squared theta, and then the square root of x squared again, plus 4, and then dx turns into this, so 2 secant squared theta d theta. That's what our integral transforms into. Okay, and then we use the same trick that we've seen here a lot. We factor this 4 out so that we get 1 plus tangent squared. And then we use the fact that 1 plus tangent squared is secant squared to turn all of this into 4 secant squared. This is why this substitution was the one that we made. Okay, now when we split the square root into each piece, this becomes 1 over 4 tangent squared, and I might as well put this in the numerator. So 2 secant squared. I'll have my d theta floating out in front. And then so 4 tangent squared times then the square root of 4 here, so this breaks up into root 4 root secant squared, right? You just split it up into 2 different square roots. Well, the square root of 4 is just 2. And that cancels out with this 2 here. And then remember the integral of, the square root of something squared in general is the absolute value of x. So this turns into the absolute value of secant theta. But because secant theta is 1 over cosine theta, and we already talked about how cosine is always positive between these angles, 1 over cosine, so 1 divided by a positive number, will also be positive. So we can just drop this absolute value free of charge. we don't have to tack on the additional minus sign possibly. So we drop this free of charge. And then this just becomes now, after one of the secants cancels out, so this cancels out and this turns into a 1 first power, we're left with 2 secant theta all over, oh sorry, the 2 is gone. So secant theta over 4 tangent squared d theta is what we're left with. Now that's the only piece of information we'll want to hold on to. So then this dividing by 4, I'm going to write as a 1/4 out in front. Okay, so we have that. Now at this point we may start to think, what can we do a substitution at this point? So there would be 2 options. One option would be let u be tangent, in which case du would be secant squared, and then du over secant squared would be d theta. So we would end up dividing by secant squared, and that wouldn't be good because it would cancel out with this, but it would pop up an extra secant squared in the denominator, which we don't want. So this choice, not the best one. Now if we try let u be secant, then du would be secant theta tangent theta. So then du so then when we replace d theta with this, things would actually be bad. We'd be hitting this tangent theta with this tangent squared and getting a tangent cubed, and so this is also not a good choice. So at this point we may want to try to use some things that we know from trig. And so we're going to rewrite this as, we're going to write secant, the numerator, so we'll write this as secant theta times 1 over tangent squared, just splitting this apart. And now we'll write secant as 1 over cosine, and we'll write 1 over tangent squared as cotangent squared, right? Because 1 over tangent is cotangent. They're reciprocals of each other. And then we'll rewrite cotangent now instead as cosine squared over sine squared. Because remember, cotangent, just regular cotangent, is cosine over sine. So squaring this, you pick up a squared on each term. And then we have our d theta. Okay, why is this nice? Now this becomes 1/4 integral. One of the cosines cancels out, and this just becomes the first power. So this becomes 1/4 cosine theta over sine squared. And now we can do u substitution. So now if we let u be equal to sine theta, this would give us that du is cosine theta d theta. So du over cosine is d theta. And this is perfect now because we'll have 1/4 the integral of cosine theta over u squared du over cosine theta. And then this cancels perfectly. So then we're left with 1/4 integral 1 over u squared, right? But I'm going to rewrite the 1 over u squared as u to the negative 2, and then we could just use the power rule. So this will be 1/4 u to the negative 2 plus 1 over negative 2 plus 1. And so this becomes a negative 1/4, because negative 2 plus 1, this is just a negative 1. So this just introduces a minus sign. And then we'll get u to the negative 1, which is 1 over u technically. So then putting this all together, we get a negative 1 all over 4u plus c. And then going back to the original variable, this is negative 1 over 4 sine theta plus c. But we're not done yet, because this is in terms of theta, and we started out with x's. Because remember, x was 2 tangent theta. That's what the original substitution for x was. Is that correct? Yes. Okay, so then how did we figure out what x is? Remember, we drew a right triangle. Out of this piece of information, we know that if we divide both sides by 2, x over 2 is equal to the tangent of theta. This means that if I label this angle theta, the opposite is x and the adjacent is 2. Remember, tangent is defined this way. It is the opposite divided by the adjacent. So x over 2. And then if you use the Pythagorean theorem, we know that this squared plus this squared should be equal to this length h, the hypotenuse squared. So then this is 4 plus x squared, and then taking the square root to get rid of this tells us what h is. So h is the square root of 4 plus x squared. And now we're in business, because now we know what sine is. So this is negative 1 over 4 times the sine of theta is opposite over hypotenuse, so x all over square root of 4 plus x squared plus c, which this becomes negative 1 over 4x over this, right? Because you can think of 4 as 4 over 1. And then multiply the numerator, multiply the denominator. And then this essentially, 1 over all this is the reciprocal of this. So we just flip this guy and we'll have our final answer. So this ends up being negative square root of 4 plus x squared. And that's the integral of what we started with. Let me make sure the integral's right. 1 over x squared. Yes, okay. So yeah, this is our final answer. So yeah, it looks kind of wonky, right? It's pretty crazy. We can find out the integral of this. It's quite amazing. And the trigonometric substitution is what allows this. Okay. And then let's maybe. Okay, and now let's do one more example with the tangent substitution. So now we'll have a definite integral. Or sorry, not. We have 4x squared plus 9 to the 3 halves. Yes. Okay, so now let's just do a little bit of algebra on the side. We know that 4x squared plus 9 to the 3 halves is the same thing as the square root of all of this cubed. Because 1/2 does a square root, and then that result, you can cube that. And that's the same thing as taking the 3 halves power. So we know that that's what we're working with.
So we have 4x squared plus 9 square root of this cubed. And now we want to think about this in terms of an x squared plus a squared. The problem is we have something in front of our x squared. So let's fix that by just pulling it out. So we take the square root of 4, factor that out, and now this becomes 9/4. And then this becomes the same as, you can split the square root up, so we get root 4 times this. But I'm going to write 9/4 as 3/2 squared. Okay, and then root 4, we all know that to be 2. And now that's perfect because this is in the form x squared plus a squared, where my a is 3/2. So this is going to be my choice for a. So I'm going to let x be equal to 3/2 tangent theta. And as a result of that, dx will be 3/2 secant squared theta d theta. Okay, and so now the other thing that we want to do is figure out what these new limits of integration are. So if x is equal to 0, I have 0 equals 3/2 tangent of theta. And just dividing by 3/2, this tells me that 0 is the tangent of theta. So tangent inverse of 0 is what theta is. Remember, anytime we have an expression like this, we can apply the inverse function analog to get this guy. Because see, what are we saying? We're saying that here is some angle in my domain, theta, and under tangent it went to 0. This means that if you stick this into inverse tangent, that the inverse tangent of 0 should be equal to theta. Okay? But we know that what angle goes to 0? Under tangent, it's 0. We know that the tangent of 0 is 0, so the inverse tangent of 0 is the same thing. And so this tells us that theta is 0. Okay, so that's one limit of integration. And then similarly, if we let this be 3 root 3 over 2 with a little bit of algebra, aka multiplying by 2/3 on both sides, cancels out here and cancels out these guys. So we're just left with root 3 equals the tangent of theta. Now it's the same thing. We know that pi over 3, if you stick that into tangent, this gives you root 3. And so the answer to what theta is the tangent inverse of root 3. And just looking at that, tangent inverse of root 3 is pi over 3. Okay, so that's our second limit of integration, is pi over 3. Okay, so we recovered that. So we now know the integral goes from 0 to pi over 3. And this x cubed becomes the cube of this. So 3 cubed is 27. All over 2 cubed was 8. And then tangent cubed here. And then all of this times, on the bottom, this is what we have. The bottom is this, so it's 2 times the square root of x squared, which is 9/4 tangent squared, plus this guy, 9/4 over here. And then all of this is cubed. And then we have dx, which is the 3/2 secant squared theta. Running out of room here. have secant squared theta d theta. Okay. Okay, so then now this is, so this 2 will cube it, so that'll come out as an 8. Right, because we're cubing this expression and this expression, so that'll be an 8. And then we'll still have the square root of all this cubed. This is still cubed. But remember, we're just going to pull this 9/4 out to just turn this into 9/4 tangent squared theta plus 1. And the reason we do that is that this is now secant squared. So this really reduces to secant squared. Okay, and then we take the square root of this, which is 3/2, and the square root of that, which is just secant. So now we really just have 3/2 secant theta squared, or cubed, I'm sorry. Then times the other 3/2 secant squared theta d theta. Okay, so now we have that. We go up here. So now this is the integral from 0 to pi over 3. (27/8). And now I'm going to rewrite this in a more suggestive way. So this will be 27 tangent cubed all over 8 over, now this 2 when I cube it will be an 8, and that'll cancel out with this 8 here, because I'll have 8 times 3/2 cubed is 27/8, and the 8 will cancel. So I just have 27 here, and then secant cubed, and then this guy. And now I'll write this as over 1. So we have a fraction over a fraction. How do you fix that? You multiply by the reciprocal of the bottom. So this will turn into 0 to pi over 3 times 1 over, because that's the reciprocal of this, and then times 3/2, and I'll write it like this. So I'll write this as 3 secant squared theta over 2. Just so it's very suggestive. Okay, so then now the 27s cancel. And then this secant cubed reduces just to a secant once this cancels. So what am I left with? Now I'm left with, let's see. So this 3 on top, 8 times 2 is 16. So that's a 3 over 16, which I'll pull out in front. And I just have tangent cubed over secant. Okay, very nice. So now any type of substitution won't help us in this case. I'll let you guys think about why U substitution won't help in this case. So we'll want to do some trig to make this look a little different in hopes of getting a different answer. So tangent, so I'll rewrite this as tangent cubed times 1 over secant, right? Because if you multiply this, you get that back. Now the advantage of that is tangent cubed is sine cubed over cosine cubed, and 1 over secant is just cosine. So then this cosine cubed hits that 1 over cosine cubes hit this goes away, and this becomes cosine squared. So that's what I'm left with. So again, u substitution won't be super helpful here. So what we're going to do is we're going to rewrite this guy first and then do u substitution as sine squared times sine, and then use the fact that sine squared is actually 1 minus cosine squared. So we're going to write this as 1 minus cosine squared times sine. And now u substitution will work. Now if we let u be equal to cosine theta, du will be negative sine theta d theta. And so we know that du over negative sine is d theta. And that's really good. And now again, if we have to change these variables, so u at 0 is the cosine of 0, which is 1. And then u at pi over 3 is going to be 1/2, because it's the cosine of pi over 3. So that's 1/2. Okay, so then we get 3 over 16 integral from 1 to 1/2, right? That's the order. And when we flip this, we'll flip it and tack on a minus sign using that really old property of the integral, which is really cool. So this is 1 minus u squared, and then that's just sine, and then this is now u squared, and then we have du over negative sine, which is perfect because this cancels. And then this minus sign will come out in front. Okay. And then in order to flip this, so I go from 1/2 to 1, I tack on a minus sign, right? So if I tack on an extra minus sign, effectively making this a plus, I can switch this from 1/2 to 1, which is cool. We haven't used that trick in a while. And then now we'll divide this u squared into each term. So this will be the same as 1 over u squared minus u squared over u squared. And then now, this is just u to the negative 2, and this is just 1, and we're ready to just crank this out. So this becomes 3 over 16 times, when you use the power rule, this becomes negative 1 over u, and then this becomes minus u, and you evaluate that from 1/2 to 1. And then when you do this, finally, the answer you get becomes, let's see, did I mess something up? Book has this in slightly different order. Yes, never mind. They didn't flip their limits of integration, that's why. So yes, once you do this, you'll get the final answer of 3 over 32. Okay, awesome. So that is another example with the substitution that involves tangent. So we'll do a little more next time, and I'll see you guys then.